In this section, we'll look at a subset of covalent bonds called polar covalent bonds, and then we'll look at molecular polarity and molecular attractions. So when you have covalent bonding, you have two different kinds of nonmetals, and they will share the electrons that they're bonding with, but they kind of share at times the way an older brother might share candy with a younger brother. You end up with some uneven sharing taking place. So nuclei, because they have positive charges in them, have a pull for the electrons that are shared. And some of them pull a lot stronger than others. So fluorine is your strongest polar. You'll notice on this Pauling electronegativity values chart, fluorine has a 4.0 beneath it. That's the highest number you can get for electron pull. And the lowest number is found on these noble gases off to their right. They have no pull. They don't want any, they don't want to give up any, so they've put no number underneath them. And then you'll notice rubidium and potassium here have 0.8. They're located in the lower left. They're the blue, dark blue areas here. So they have almost no pull for electrons. That's because they want to give them up so that they can become like a noble gas in how many electrons they have. And fluorine really desperately wants to have it. So the question is, why is it that fluorine has more of a pull than chlorine? And the answer is the electrons that you add in when you do the bonding are located closer to the nucleus, because the size of a fluorine is smaller than the size of a chlorine. And so just as when you bring two magnets closer together, they have a stronger pull, just as you bring bonding electrons close to that fluorine, the nucleus will have a stronger pull than a chlorine would, which is slightly bigger. So it's like having those magnets located further apart from each other and checking for a pull there. What this means is that since they don't share equally, you end up with a charge on your bonding. So one side of your molecule will be positively charged because it's kind of losing out on that sharing. And a lot of the electrons are actually spending their time around the other atom. And that other atom that has more of those shared electrons located around it is going to be slightly negatively charged because it's got an overabundance of electrons going on there. At its extreme, you can get some really strong pull there. At the other end, when you combine two elements of the same sort, that sharing is going to be pretty much equal, and you won't get a charge on either end of things. So for example, I could take two fluorines, most electronegative element on the periodic table. So you look at that and you're like, oh, this is going to be polar. But if you combine it with another fluorine, well, they both have a really strong pull. So it's kind of like playing tug-of-war with two equally strong men on either end. Nothing goes anywhere. So that sharing ends up taking place equally, and you have what's called a non-polar bond. It's not polar. But if you take hydrogen, which is not as electronegative as fluorine, and fluorine, and you put those together, then you have the fluorine pulling that electron more that's shared between the two electrons that are shared between the hydrogen and the fluorine. Most of the time, those two spend their time around the fluorine and almost never spend it around the hydrogen. So the shared electrons spend their time around fluorine. Fluorine gets a negative charge, and they don't spend a lot of time around the hydrogen, so the hydrogen gets a positive charge. Now I'd like you to pause this and go through here and try to predict, will there be any charge between these two things bonding? If there isn't, then you just write nonpolar. If there is, draw an arrow with the arrow pointing towards the element that has the negative charge. Which one is going to hog the electrons? When all the bonds of a molecule are nonpolar, then the molecule is also nonpolar. So if you have H2, O2, F2 equal sharing, nonpolar, the molecule is nonpolar. So if you have a polar bond, and there's only 2 atoms connected, then the molecule is polar. That kind of makes sense. Here we have hydrogen and chlorine. The chlorine swipes the electrons. You'll notice the arrows pointed towards chlorine, and they often will put a hatch on the right side here of the arrow because that's the positive side of things. So notice they put a positive sign there. And so the electrons are spending their time around that chlorine, and the hydrogen is left positively charged. So this would be a polar molecule. When there's 2 or more electrons connected to that central element, then it can be a toss-up. Then you have to figure out whether it's polar or not polar. So here we have boron trifluoride. It forms a planar molecule with 3 things on the outside. In this case, fluorine. And you have boron in the center. And the fluorine is, of course, more electronegative. It's the most electronegative thing on the periodic table. And it's going to hog the shared electrons that are in that bond. Your boron in the center is going to be left without the electrons that it's donated for most of the time. And so it gets a positive charge. And the ones on the outside all end up with a negative charge. But if you were to do the math for these arrows pointing off, you'll notice that because they're all evenly spaced, they cancel each other out. If you can imagine a tug-of-war with 3 strong men all at 120 from the center and some poor soul in the middle and they're pulling, that person in the middle isn't going to go anywhere because they all pull with equal force. So although these bonds are polar, the molecule is nonpolar because the bonds cancel each other out mathematically. But sometimes those bonds don't cancel each other out. Water is a great example of that. You have lone pairs that kind of push those hydrogens close together. The non-bonding electrons push those hydrogens close together. It's at a 105-degree angle, and so those hydrogens kind of donate into the oxygen, which is more electronegative, and the oxygen ends up negatively charged, and the hydrogens end up positively charged, and overall the molecule has a negative side and a positive side. And sometimes you can have a molecule that would cancel out. This one off to the right is called a tetrahedral. And if the same thing were attached to all of these bonding sites on the outside, it would cancel each other out, even if it was polar. But if you put something different from the identity of some of the others, then they don't cancel anymore. So for example, hydrogens would donate into the carbon, electronegativity-wise, but the chlorine is going to take from the carbon. So overall, you've got this force pushing towards the carbon and up towards the chlorine. So the chlorine is negatively charged, and the lower part here is going to be positively charged. And so this is a polar molecule. So you have to do kind of this 3D imagination of how the tug-of-war would all solve out to figure out if the overall molecule is going to end up polar. So that's within a molecule that we've just talked about. Now we're going to start talking about between molecules. If there were no attractions between your atoms or between your compounds, then everything would just separate out to infinity. But because there are attractions, we do get liquids, and we do get solids, and we do get gases that stick around a bit because they attract each other. So you have various types of attractions that happen between molecules, and some are stronger than others. So for example, you can have an ion dipole attraction. That's when you have a positive or negative charge, usually from an ionic compound, and you surround that with a compound that is polar. So here we have sodium. This sodium ion is surrounded by water molecules with their oxygen sides, which are the negative side, pointed towards the positive sodium. That's an ion dipole, and that's what allows you to take like a bit of table salt and stir it into water and have it dissolve, is that the ions will actually separate and be stabilized by the charges on waters. But notice it takes more than one water to stabilize the sodium charged. So they all surround that sodium. Another possibility is hydrogen bonding. Now this plays a huge role in nature. It holds DNA strands together, it holds protein strands together, and what happens there is you get a compound that has nitrogen with hydrogen, hydrogen with fluorine, which there's only one of, it'd be HF, and oxygen with hydrogen, water, alcohols, things like that. They've got to have at least one OH on them where the oxygen is actually literally bonded to the hydrogen. So any of those three will bond in what's called hydrogen bonding, where the negative part actually forms an almost real bond to a neighboring hydrogen that is not part of the molecule. Those are fairly strong attractions. And then you have dipole-dipole, which is where you've got two compounds that are polar, so they've got a permanent partial plus minus in them, and their plus minus parts will attract each other. So here we have an oxygen that's negatively charged. It's attracted to the positively charged hydrogen of chloroform, which has a CH side and then 3 Cls pulling away from that. That would be called a dipole-dipole attraction. And then we have our ion-induced dipole, which is where you have a full charge, and that full charge will actually take something that isn't charged at all and cause its electrons to kind of pool to one side because the electrons are attracted to the charge, or move away because the electrons are repulsed from the charge. In this case, we have Cl- and hexane. Hexane's nonpolar. You have your Cl-, which is negatively charged, and so that's going to cause the electrons in this hexane to move slightly away from the chlorine. It'll move, in this case, to the right side of the picture to get away from the negative charge, because negative charges repel. And electrons are negatively charged. This chloride ion is also negatively charged. We can also have dipole-induced dipole, which is where you've got something like acetone that's polar. It doesn't have a full plus or minus charge like your ions do, but it has a partial one. And in this case, our oxygen is the most negatively charged. If it comes up to something like our hexane, which has no positive or negative charges, it'll cause the electrons to once again pool away from the acetone, which will create a partial negative charge on the right side, partial positive charge on the left side. That's just temporary. It's not super strong, but it's being influenced by what's around it. And then you've got dispersion, which is where you take two nonpolar things, and those electrons will constantly be moving, but because there's something next to it with electrons, they'll interact, and at times they'll start pooling their electrons in the same directions at the same time, so that when one side is positively charged, the side next to it is negatively charged, and you get a slight attraction there. And those attractions increase the bigger your molecules get. So like methane, it isn't strong enough to hold two single carbons with hydrogens together, but you get really long chains of carbon and hydrogen, and because they're so long, they don't move very much, and that pooling can take place in ways that last a little longer, and you get the road sludge that they use to kind of fill in cracks. So those are really long carbon chains that have just dispersion attractions taking place in them. So the bigger your molecular size, the stronger those dispersion forces can be. So let's look at a few of these again in closer detail. Ion dipole, this is your strongest attraction between molecules. Remember, if you have ionic, then the ionic attraction is just part of the ionic molecule. So the strongest attraction between molecules, it occurs when you have an ion compound that dissolves in a polar solvent. And when that happens, the solvent orients its negative charges around the positive ion and orients its partial positive charges around the negative ion. So here we have water, and it's surrounding, or some other molecule with a dipole, and it's surrounding a positive and a negative charge. Hydrogen bonding, you have to have F, O, or N bonded directly to hydrogen. They can't have an element between them. They have to directly be bonded to each other. So water is a great example of that. It's got oxygen, it's got hydrogen directly bonded to it. And what that does is it creates such a strong plus and minus offset The negative will form an almost real bond to a neighboring hydrogen in this case. Same thing happens with fluorine or nitrogen if it were in this position here. Because of hydrogen bonding, we get a unique property with water. Usually when things are frozen or in the solid state, they are more compact. But water is not that way. If you take water and you put it in its solid state with its liquid state, the ice melts on the ice floats on the top. And the reason it does that is because it's less dense. And the reason it's less dense is the water molecules do hydrogen bonding. And when they do hydrogen bonding, they form this lattice with these large holes in the lattice, and so it spreads out. That's also why when you freeze water, it expands. Then we have our dipole-dipole attractions. There you have two polar molecules, and they orient so that the positive side goes next to the negative side of the neighboring molecule. It's stronger than dipole-induced dipole, but it's weaker than hydrogen bonding. When you have dipole-induced dipole, you have something that didn't have any polarity plus-minus wise. But when you bring something that does have a plus-minus polarity next to it, it will cause the electrons to kind of shift away from the negative side or attract to the positive side. And so you've induced a dipole. And that induced dipole may induce a dipole in the molecule next to it, and it kind of becomes this chain reaction in 3D. It's weaker than dipole-dipole because this is just pushing it into that position and then causing the chain reaction. And it can move over time as the molecule next to it moves. Of course, its induced dipole is going to shift. So it's a weaker attraction, but it still is an attraction. And the larger your molecule gets, the more electrons it has to do the pooling, the less it's likely to move quickly, and you'll get a stronger molecular attraction. And then the weakest is going to be your induced dipole. Neither one really had a plus-minus to begin with, but at one moment, one of them tends to have a little bit of it in one direction, and that influences the one next to it to have a little bit of that same orientation, and they'd be constantly on the move as to where that plus and minus is located in the molecule. And that would influence the one next to it, and it just keep changing, but it does cause an attraction between molecules. Once again, the bigger the molecular weight, the stronger this attraction is going to be. So go ahead and look through these. If you went ahead and predicted polarity, see if this matches the answers that you had for your polarity